Hi, my name is Ellery. Today I'm going to present my Planetary Exploration seminar, which is Motor Drive for Planetary Exploration System. The video that you have just seen was recorded by the rover Perseverance on the planet Mars. This presentation is based on a book written by Ellery, which is titled Planetary Rover Robotic Exploration for Solar System. In this presentation, I'm going to discuss the type of motors used for the drive system in the planetary exploration rovers and make a way or give a clear idea how to choose the proper type of motor for such a mission. And the author of the book has mentioned 4 main criteria on how to choose the proper motor for the rover. And these criteria are low rotor inertia, low mass, high torque, and high positioning accuracy. And if you examine these criteria carefully, you will notice that the main or the most important one is the low rotor inertia. Because if the motor or the rotor has high inertia, it means probably that it has high mass, and it will reduce the torque of the motor. This will also affect the positioning accuracy, as the control system try to stop the motor at a certain position or certain angle. The motor will keep on rotating because of the high inertia. And to overcome this problem, the author has mentioned one main solution or one main consideration to take into the motor construction, which is the rare earth permanent magnet. By including the permanent magnet in the construction of the motor instead of the electric magnets, we can reduce the volume of the motor by up to 70%, and we can increase the efficiency of the motor by 50%. And mainly there are several types of permanent magnets that can be used, but 2 types of permanent magnets are highly recommended, especially for space missions. The first one is neodymium. Neodymium has strong magnetic density, and it's not very expensive, and it's used for many types of motors, high performance motors. But there is one problem with neodymium, is the operation temperature. If the neodymium magnet is exposed to a temperature higher than 80 degrees, it would lose their magnetic density. Therefore, depending on the thermal isolation system, whether the motor is properly isolated from high temperature, we can consider whether to use or not neodymium. Other solution is to use samarium cobalt. Samarium cobalt isn't as much stronger as the neodymium, and it's much more expensive. But it's widely used for space missions because it can operate at a very high temperature, up to 200 degrees. By including this in the construction of the rotor or the motor or the stator, the performance of the motor can be much higher, and the motor can be suitable for space missions, namely planetary exploration rovers. With that being said, we have 4 types of motors that mainly include rare earth permanent magnets in their construction. And the first one is the stepper motor. Stepper motor has been used for planetary exploration rovers, but not for the drive system, because stepper motor provide high positioning accuracy, and it can be controlled with an open loop system. It doesn't require closed loop control. It has high torque, but at a low speed. If we increase the speed, we're going to lose the torque. That's why it's not used for the drive system. The counterpart for the servo motors is the counterpart for the stepper motor is the servo motor. Servo motor overcome the problems that exist in the stepper motor, but servo motor is nothing but a brushed DC motor with compact electronics and small mechanical system to regulate or to control the position of the shaft of the motor. That's why I'm not going to discuss the servo motors. Plus, neither stepper motor or servo motors are used for the drive system of the rovers. that are used for other systems. For instance, the camera positioning system or the antenna positioning system. This leaves us with two types of motors that we can use for the drive system. The first one, and the most common one, if we check the previous missions, is the brushed DC motor. Brushed DC motor has a simple configuration with two wires control. We can control the speed of the motor by controlling the DC voltage at the end of the wires. Second advantage, it's ideal for extreme environments due to the lack of electronics. Brushed DC motor doesn't include any complex electronics, doesn't need any sensor feedback. But the problem with the brushed DC motor is the commutation system. This commutation system reduces the lifetime of the motor because it's based on the brushes that are made of graphite, and graphite requires humidity and oxygen to maintain a longer lifetime, which is not available in Mars, for example. The second type of the motors that we can use is the brushless DC motor. Brushless DC motor has a longer life and can provide higher torque, and it comes with a lighter weight if we compare it to the brushed DC motor. But this is because of the usage of complex electronics, and this can be problematic in the design because electrical system or electronics needs higher protection than mechanical systems in space applications. And there is a second problem, which is the sensor feedback. In order to control the brushless DC motor, we need to know the exact position of the shaft of the motor. And this is done by using a sensor to measure or to sense the position of the shafts. And usually sensors are very sensitive, and using a sensor in the system can be problematic in the space environment. In this slide, I'm going to briefly discuss the working principle of brushed DC motor. Brushed DC motor consists of a rotor, stator, and a commutator with brushes. When current flows through the armature winding, a magnetic field is generated, causing the rotor to rotate. The brushes make contact with the commutator segment, allowing the current flow to change direction at the right time to enable rotation. And finally, the speed of the rotor can be adjusted or can be controlled by adjusting the voltage of the DC supply. And the problems with the brushed DC motors is the existence of this brush system. The spring-loaded carbon graphite brushes create friction and wear out with usage, especially in vacuum, because graphite brushes need humidity and oxygen, which is available in the Earth's atmosphere. And this humidity and oxygen will build up a hardened patina on the surface of the brushes. In the absence of the humidity, the brushes will wear out very rapidly, which is the situation in the Mars surface. And this was noticed during the testing for the Viking lander camera system, which was based on the brushed DC motor. There is another problem with the brushed DC motor, or another phenomena which is called sparking. In theory, a brushed DC motor can rotate up to 20,000 RPM, but in reality, we can't exceed 10,000 RPM because of the commutation system. If this rotation speed is too high, sparking will happen, and the current flow from the DC voltage to the winding will be limited. Even though all the problems that were mentioned with the brushed DC motors, it's still the most common solution for the drive system in the rovers. And this is because of the solutions that were discovered over the years. And we're going to discuss two main solutions. The first one is to replace the carbon graphite brushes with precious metal brushes. This might be an expensive solution, but it limits the friction caused by the carbon graphite brushes, and it has a very low voltage drop over the commutation system. But the problem with this solution, it has very low current flow. So if the motor needs to operate in high torque, this isn't the proper solution. And there is another problem is with the continuous working mode, because the precious metal brushes doesn't allow switching between clockwise and counterclockwise rotation of the motor frequently. So depending on the mechanical design, whether it needs a high torque, whether it needs moving forward and backward by switching the rotation of the motor, this can be applied or not. A different solution is to use graphite brushes made of different alloys. Instead of using carbon graphite brushes, we can replace the carbon by silver or copper graphite brushes. And this will allow a high current dynamic mode, because with this solution, the motor can rotate in clockwise and counterclockwise easily, but it also has a higher friction and high audible noise. As long as the friction doesn't limit the lifetime of the motor, this solution is the best known solution for the drive system for the rovers. And in the picture below, we can see an experiment that was done for the ExoMars drilling motor tests. In this picture, we can see three types of graphite brushes made of three different alloys. The first one is graphite carbon brushes, and the second one is graphite copper brushes, and the third one is graphite silver brushes. And the motor was working continuously over weeks. And in the first picture, where only carbon graphite was used in the vacuum environment, the brush was worn out completely in 3 days. And the second solution, where the copper graphite is used, this lasted for 1 week. And the third solution, where silver graphite is used, this lasted for 3 weeks. And for the conventional usage or the lifetime of brush DC motor, this was more than enough. When it comes to selecting between brushed and brushless DC motor, there are another two aspects that we should take into consideration. These aspects are the speed and the torque, and the second aspect is the operation mode. As a starting point, let's take a brushed DC motor of a given size. Typically, the maximum speed of a DC motor can be as high as 10,000 RPM, as discussed earlier. At this speed, the service life is strongly reduced due to the increased electrical and mechanical wear. A brushless DC motor of a similar size and similar magnetic design can be operated at much higher speed, reaching up to 100,000 RPM. Meaning, if the mechanical design of the rover includes transmission system with a high ratio, which is the case in most of the rovers, using a brushed DC motor will extremely limit the speed of the rover. The second aspect is the motor drive, the motor operation. When it comes to the motor operation, brushed DC motor has the simplest operation mode. On the other hand, operating a brushless DC motor is very complex, but it comes with the luxury of precise control of the torque and speed of the rotor. And if we have a mechanical transmission system with a high ratio, the precise control of the torque is no longer needed. After choosing the type of the motor, we should carefully select the parameter of this motor. And the author of the book has listed several requirements to precisely select the parameter of the motor. The first requirement is to estimate the gear ratio needed for the rover. And the gear ratio can be calculated by this formula, which is N equals the square root of the load inertia divided by the motor inertia. And the second requirement is the load requirement at the motor shaft. And this includes the transmission, the friction resistance, and the acceleration torque. With the load requirement being defined, we should examine the torque speed curve to find out the maximum voltage needed to operate our motor. And there is also several rules, such as the peak torque that should be 2 to 3 times the maximum load torque, and the torque constant Km, which relates the power losses in the winding to the motor torque output. That can be calculated by the formula, the torque divided by the square root of the winding power losses plus 15% margining. This margining is due to the heating problem. With the high heat, the power losses of the motor will be higher. That's why we should add approximately 15% margining. And there is also back EMF resistance, which is opposing the voltage generated by the back EMF of the motor. And finally, there is the parameter of the motor performance quality factor. The last part of this presentation is dedicated to present several Mars exploration missions and emphasizing on the type of the motors that were used on these missions. And the first mission is Viking 1 and 2. These are two identical spacecrafts, each consisting of a lander and an orbiter. Even though that it didn't include any rover, but it was essential for the following missions. And in this mission, a brushed DC motor was used for the sample acquisition system, drilling into the Martian surface to collect soil and rock samples. And there was also a stepper motor used for the sample handling system by precisely positioning the robotic arm and its various instruments, allowing accurate sample analysis and experimentation. And there was also a brushless DC motor for rotating the camera housing and moving the scanning mirror. This mission was launched in 1975, and the end of mission was in 1982. The second mission is Mars pathfinding, and this mission included a rover which called Sojourner. It was launched in 1997, and it lasted only for 3 months. And there was 11 brushed DC motors that were used in this mission, and the design of the motor was based on the precious metal, using precious metal brushes and neodymium magnets. As discussed earlier, precious metal brushes doesn't allow high current flow, and that's why the current of the motor of the drive system was 116 milliamps with the very high gearing ratio going from 2000 to 1, and very low torque with a maximum of 1 Newton for the front wheel and 0.5 Newton meter for the rear wheel, and no load was expected on the middle wheel. And there were several modifications made for the motor to be able to function in the Mars environment. Namely, they used titanium and fiber carbon for the structure of the motor to mitigate the thermal expansion. And they used the capacitor to limit the sparking phenomena. And the total distance covered by this rover was 100 meters. And for this 100 meters, the rover or the motor had to rotate 0.5 million rotation. And this is due to the high gearing ratio. The last mission that I'm going to discuss in this presentation is the famous Mars Exploration Rover with the two rover Spirit and Opportunity. This mission was launched in 2004, and it lasted up to 2010 for the rover Spirit and up to 2019 for the rover Opportunity. And the design of the motors that were used in this mission was brushed DC motors with graphite brushes. And if you remember from the previous slide, graphite brushes can allow very high current flow. That's why the maximum wheel load for the drive system was 90 Newton meter with 2 amps current flow. And the gearbox or the gearing ratio is 1500 to 1, which is still very high. And the total distance covered by the rover Opportunity was 42 kilometers. And each rover contained 39 motors for the various applications, including the drive system, the steering system, the solar array deployment, the camera, and the robotic arm. And it is worth mentioning that the end of life or the end of mission for the rover Spirit was because of the failure of one of the motors of the drive system. And with the design that included a gearbox of a ratio of 1500 to 1, if one of the motors fails or is no longer functional, this will mean that the gearbox will be in brake mode, so the rover won't be able to spin or won't be able to move.